Okay, cool. So in astronomy, we often have a situation where we have an observed spectrum from a telescope, and we want to compare that to our understanding of physics. That's usually in the form of a synthetic spectral model. The problem is that often those models are rigid. In other words, it's really hard to model the true spectrum of stars, and so you can only compute those on discrete grid points. In other words, you can't have like a flexible, tunable model where you can on the fly compute the full spectrum of a star, at least not typically. So what we have are these precomputed synthetic spectral models that look like this. They're really high resolution and have tons of our knowledge of physics encoded in them, but you can't turn knobs to change them, or at least not continuous knobs. So you only have discrete knobs by jumping to, say, 100 Kelvin further hotter or cooler in temperature, or more or less surface gravity, but only on discrete points where these have been computed. So what we want to do in this notebook is clone those precomputed synthetic spectral models and do so in a way that we can tune those models, at least the features of those models continuously. So in other words, we could take individual spectral lines and turn them up or down because those lines may look different in reality compared to our expectations from models. So here's how we are going to go about that. So in this first notebook, we're going to just use heuristics. So we're using SciPy, and we're going to say, find all of the lines, all of the spectral lines. In this case, we use the find peaks method in SciPy. And we find all of those peaks, all of those spectral lines. And in this case, we found 1,258 of them, which is sort of a lot, but considering that this spectrum is so rich, it's a significant reduction in the amount of numbers we have to specify to describe this spectrum. So we also find the prominence of those peaks, so sort of how deep they are, and then the widths of those, so how wide each spectral line is in terms of like a width. And then we can compare that to data. So how well did our peak finding do? And it looks like in this real spectrum in green, we basically see real, genuine stellar atmosphere structure at each of these points that we found in the peaks. We don't find all of the minute peaks because those aren't prominent enough according to our threshold. So this process works good enough. By the way, you'll notice that our individual line strengths don't actually match the models perfectly, which is part of the problem we're trying to ameliorate here. Cool. So if we then feed all that peak information, that heuristic coarse peak information into, say, a Lorentzian line profile and say, okay, make Lorentzians at all of those locations with those strengths and widths, you get something that's close to the real spectrum, but actually sort of not that great. And that makes sense because we're just starting with heuristics. Those heuristics don't necessarily exactly describe a Lorentzian, and we also don't have the exact continuum shape well specified in this first pass. But that's okay, because what we're going to do in the next notebook is try to reduce that error by tweaking each individual line shape with a relatively new technology. So that's what we do in this notebook, which is to use a relatively new technology called PyTorch, which is actually fairly popular within the artificial intelligence, neural network, machine learning community. And that allows us the ability to treat each spectral line as if it's like a weight of a neural network. And it also allows us to use GPUs, which accelerates the whole thing. So we'll do everything exactly the same as before, but we're going to add this new module, this new Python class, which is based on a neural network module from PyTorch. And this is just an emulator class. And all it says is, okay, with the starting points that we had from the heuristic of the amplitudes and widths and line centers, let's adjust the amplitudes and the widths of every single spectral line through a process called stochastic gradient descent, but basically just find how changing each of those would improve our model fit, and just do that that process iteratively. Forward model the spectrum with all of that information, and then we're going to tweak the model in response to a target spectrum, or in this case our known precomputed synthetic model. So let's try to do this live. So I'm going to say go ahead and run that training process. So this will be now a neural network training process. We can bring that up. We actually have a tensor board, which is like a live view of the training process. And here we go. It's now gonna get underway. We can hit refresh, and then we can look at like a time series of how the training is going. And what you'd like to see is that the loss, which is like the mean squared error of our spectrum cloned versus the target, should go down. And in fact, that's what we're seeing. So that's a good thing. And we can keep hitting refresh. But let's take a look at the actual spectrum. So the native Phoenix precomputed synthetic spectrum, which is our target spectrum we're trying to clone, is in orange here. And the beginning point in blue is actually pretty bad. So at the very beginning, we start with a bad guess, or not very close to the target. But as we're training, we're going to see that this gets better and better. And already after 50 training steps, it looks like we're much better, but still not great. So this is the residual of our target precomputed synthetic spectral model compared to our clone, and we want to see that residual gets smaller and smaller, and it does. So we're making good progress. So again, what's happening here is every single spectral line that we've attempted to clone is getting its amplitude and width adjusted, in this case simultaneously. So all of them are changing at once. And we're also changing the continuum slope, so the black body slope here. So good. So this process is underway. It's progressing, and it'll run for 300 steps. So we can come back to this, but I'll show you sort of what the final step looks like back here when we can zoom in on how this looks. So here's what happens if you run this for much longer and even allow more lines to be modeled. So we started with 1,200 spectral lines to be modeled, but in this case, I think we used close to 3,000 or more spectral lines. So even smaller, less prominent lines were modeled. And in the end, it looks quite close. So not perfect right here. These really deep lines are harder to model because they have finer structure than what you can perceive here. And that's to be expected. But overall, quite good performance. Maybe could get even better if we ran the training longer. But this is adequate for most purposes in astronomy. And here we can zoom in. So let's just pick a small 200 angstrom snippet right in the middle of this spectrum, and take a look at how our clone compares to our beginning point, our Phoenix native sampling. And it looks pretty good, right? So we capture a lot of that structure. And now this is the key idea, is that we now have in the clone version an evaluatable function. So whereas the native Phoenix model is just sort of the pixels, here you can tweak the individual line strengths of this new model, and you can evaluate it at almost essentially any wavelength point. So not just on the grid points where the model was defined to begin with, but actually anywhere. But the key idea that's really valuable is that we're going to be able to transfer the line strengths that we learned in this process to real data. To hand in a spectrum and say, okay, here's what we think the precomputed synthetic model spectrum line strength should be, but real data shows that they're actually deeper or shallower or wider. or some combination, and we can learn sort of true physics and make this essentially a semi-empirical model later on. So we're not going to show that process now because it involves some post-processing steps that we aren't doing here, but that's sort of where this is all going. But crucially, this is where we're going now. I do want to show one example of where we could improve already this pre-training step. So this cloning process. So one thing we're doing right now is just using Lorentzians just because it's the simple thing to do to start with. But in detail, these lines are really Voigt functions. So one improvement we're going to do is basically just say convolve each Voigt profile with a Gaussian that's going to depend on each line. That's a little more computationally expensive than what we're doing now. We could also use an analytic Voigt approximation, but point is that doing so would basically fit these deeper lines better, which is an important step to do. So that's where we're headed. We can also do things like say, okay, we had our heuristic guess to start with, and then we have this refined guess. So how do those compare? And we see that there might be a bit of overfitting because essentially some weak lines that may be here, you actually do better by just making a really broad line to flatten out the line wings of this super deep line. So by including the Voigt, we should actually improve both of those effects, and that would be a good thing. Okay, so let's revisit our training, see how well it's progressed. And so if we go back to our tensor board, we should be able to see how much better it's become. So we went from 80 to now 260, and voila, we have a much better fit, and we can change our log to say our linear scale to log, and indeed we've been getting increasingly better smaller errors, so better cloning performance. And let's go to, we're almost at the very bitter end of 300 steps, and let's see, yeah, really much better than where we started. We've now essentially cloned all of the spectral lines to a degree that is, again, adequate for most applications where you're going to convolve the lines with a rotational broadening kernel anyways, or an instrumental kernel anyways. And so this process is now essentially complete, and that's good. Okay.